Hi. So I'm doing atomic force microscope measurements on CI simulant particles in ambient and vacuum conditions. So our goal is to inform the modeling of asteroid surfaces by understanding the cohesive forces, and we characterize these forces by using an AFM and acquiring force curves. Our previous work on this was done using JSC1, where we tested sphere to grain contacts at 15% relative humidity and in ambient conditions. And our results showed that the adhesion was higher at ambient relative humidity, which was because there was a water layer on the surface of the grains that affected the interaction. We quickly learned that not only does the environment or the testing conditions affect the adhesion, but also the roughness and the surface shape. For our next series of experiments, we're using Exolith Lab CI Simulant and its constituents, which consist mostly of serpentine, magnetite, olivine, and they were sieved to contain only sizes that were less than 45 microns. Before we begin to do our experiments, we characterized each sample grain and tip to acquire roughness, size, and identify surface features that may affect the adhesion. We also performed deformation tests because we wanted to know if the grains can last for the repetitions and force that we applied, and to make sure that the forces that we're acquiring was from an unaltered surface. Most recently, as in like last week, we started vacuum measurements. Okay, so for characterization of our surface, we use an SEM and a surface profiler to characterize the grains, once again, to extract size, shape, topographic info, and roughness. The left image is an SEM image of a serpentine grain, and you can see the size and surface features. On the right is our surface profiler image that uses focus variation and laser confocal to create a 3D height image. So a little bit more on characterizing the size and shape. So these are just different images of different grains of different sizes and shapes. On the top left, we have serpentine. On the top right, we have our CI grain, and on the bottom, we have a magnetite grain. And we also use the SEM to understand exactly where we placed the grains on the tip. So we also have, we use the surface profiler to extract topographic features and topographic information that may affect the adhesion depending on the contact area. And as you can see on the left, this is an example of one of the grains showing the different topography across the grain. And on the right, we see kind of a height variation 3D image. For roughness, we use the surface profiler to extract the roughness, and you can do it in two ways. You can extract the roughness over the entire rock, like the right top and bottom images, or you can extract it based on areas of interest on your sample surface, like the top left image. So these are some examples of results from our deformation tests of our 4 grains. And we did these deformation tests over 4 trials, taking over 1,600 contacts. And we observed that there was no deformation, as you can see from the series of images for each grain. But we decided to do 2 things moving forward. And that's to apply more force, and then to also apply force until we see deformation in the grains. So this is our AFM Vacuum Setup. That's on the right image, that's the AFM in the vacuum chamber, with the top lifted. And then on the left, that's the AFM in the vacuum chamber with it closed up. So these are some very, very preliminary results in vacuum at 92 millitorr and ambient conditions of a serpentine tip on an olivine sample grain. And so a note here is that these curves are uncalibrated on the X and Y axis, but there's still information that we can extract based on the depth of the dip that you see in the curves. And that's actually how we extract our adhesion. And so on the left graph in ambient conditions, we see that the dip is deeper, while in vacuum, we see a much smaller feature. In ambient conditions, as mentioned, we deal with thicker water layer than in vacuum, but in vacuum, that water layer is negligible. So we see more of a true surface interaction. But in this case, what we think is happening is that we aren't applying enough force, and we're not pushing on the sample hard enough. So the contact area is small, and due to the complexity of the rocks, the roughness, the topography, we end up with a small adhesive force. So this basically emphasizes the importance of our deformation tests and the need to increase the indent force. In summary, we've demonstrated that the AFM can be used for grain scale adhesion measurements between light grains or different grains and various sizes. We also emphasize the importance of characterizing the grain surfaces so that we can accurately interpret the adhesion results. And we predict that AFM measurements in vacuum better represent airless planetary bodies. Our initial results show reduction in adhesion visually, but that can be due to small indent force and small contact area. And we also emphasize the importance of continuing the deformation tests so that we can accurately decide if there was an increase or decrease in vacuum measurements. Thank you.
Okay, questions?
Hi, Micah Scheibel, Georgia Tech. I must have missed it, but how did you attach the grains to the tips?
Okay, yes, I did not put that in the slides. So we use an epoxy. We put the epoxy on the slide along with the grains, and we just kind of the same concept of taking the force curves, like lowering the cantilever to the surface. So we lower the cantilever into the glue and then lower it on top of the rock, and then leave it there for maybe 20 seconds, retract from the surface, and then the grain is attached. And then after that, we SEM image and characterize more of the tip. No questions?
Any more questions?
Melissa Lane. I'm just wondering what other minerals you're anticipating doing these experiments for? Are you thinking about doing them for feldspar, sweets, and things like that?
That's a good question. We haven't thought about that. For right now, we're just focusing on this, the CI simulant and its constituents, but it definitely can be done for other minerals. We just haven't thought that far in the future.